In this video, I'm going to talk about chromatography, which is an instrumental analytical technique which is a part of Unit 3, Area of Study 1 in Year 12 Chemistry. So there are 5 different types of chromatographic techniques: paper chromatography, thin layer chromatography, column chromatography, high performance liquid chromatography, and gas chromatography. The first 3 are often often used for qualitative purposes to identify different components within a sample mixture. The last 2 are not only used for qualitative purposes but also quantitative purposes. Now, there's a number of key chromatography terms that you need to understand as we go through this PowerPoint. The sample mixture and components. There are a number of components within a sample mixture, and the aim of chromatography is to separate those components out and then to also be able to identify what the components are. To do that, we need to run the components in a mobile phase across a stationary phase, and we have to elute our components either up a paper chromatogram or through a column using eluent, which eluent is a lot of the time the mobile phase, a part of the mobile phase. Now, the eluent and the sample mixture can be said to make up the mobile phase. In fact, sample mixture plus eluent makes up the mobile phase. When you run your mobile phase across your stationary phase, you get adsorption between the components within the sample mixture and desorption when the components stop interacting with the stationary phase in the paper chromatogram or the column. Another thing you need to know about are standards, and standards are where you actually know what the components are within a sample. So you'll often have your sample mixture, which is unknown, and then you might have a mixture of components which are actually known, and they are called your standards, and you compare your standards with your unknown sample mixture in order to identify the components within a sample mixture. In paper and thin layer chromatography, you have what are called an origin, which is where you actually put your sample on the paper or thin layer chromatogram, and you have a solvent front, and the solvent front is how far the solvent has actually adsorbed up the chromatogram. You also work out what's called the RF value, which stands for retention factor or retardation factor, and there's also the RF value is used in paper and thin layer chromatography, but there's also the RT value, and the RT value is used in column chromatography, and it's the length of time that it takes for the sample to go from the injection port in HPLC and gas chromatography, from the injection port to be eluted and detected in the detector. And it also stands for retention time, and they are synonymous with each other. They mean the same thing, basically. Now, the stationary phase in column chromatography can often be made up of silica beads, and that's because silica beads can have a different number of properties. They can be polar, they can be non-polar, as in reverse polarity. They can be ions, they can have ions attached to them, like sodium ions or chloride ions, or they could have, the beads can actually have holes in them, so to allow small things to get caught up in those holes in the beads. We'll talk about that more later. So, chromatography. It's a technique where a sample with a mixture of components in the gas or liquid state is run over a solid in order to separate the components in the sample mixture. Now, the sample components are separated by different levels of adsorption to the solid, which is the stationary phase. as well as different levels of solubility in the solvent, which is a part of the mobile phase. As I said, the mobile phase is made up of the sample mixture and the solvent. So you can sort of see this is a bit of a picture of that process where you've got, if you like, your sample, your solvent with your sample mixture, which is your mobile phase, which is running across our stationary phase. We think of this as the stationary phase, the second red rectangle, if you like. And if I have components in my sample, the components that interact more with the stationary phase will take longer to migrate through the stationary phase, or migrate through the column or through the chromatogram in paper chromatography and thin layer chromatography. The components that interact less with the stationary phase and are dissolved more in the mobile phase will travel faster or migrate faster through the chromatogram in paper chromatography, and they'll migrate fast in the column or through the column in column chromatography. Paper chromatography. Paper chromatography and thin layer chromatography are very similar, you'll see here. Both are where you have like a solid support, and where you've got a liquid in a jar which represents the solvent, which is adsorbed up through the actual solid support, which is paper in paper chromatography, and can often be a plastic or glass in thin layer chromatography. With thin layer chromatography, it's also important to know that not only can you detect not just by colour in thin layer chromatography, but you can also detect using UV. And so if you can't visualise your components within a sample mixture using a coloured reaction, then you can actually use UV, and this is a picture of that. So with thin layer and paper chromatography, the aim is to put a drop of concentrated sample into a spot on the at the bottom of the chromatogram, so that then you can actually run your sample up through the chromatogram. What you do then is you stand the chromatogram in a sealed vessel, such as a jar, as from the pictures before, and you carefully add solvent. And it's very important that you add solvent below the level of the sample, because you don't want to dissolve your sample in the solvent. You do want to adsorb the solvent up through the chromatogram, and because that will draw the sample with it, which will separate the components of the sample, as you can see here. With paper and thin layer chromatography, you will also have to work out the RF value, as I mentioned before, the retention factor value. And the way you do that is you have to work out the distance migrated by the solvent front and the distances of the components within the sample. And what you do then is you divide the distance migrated of a component in the sample by the distance of the solvent front. Now when you do this, you'll actually always get a value between 0 and 1. And the reason why you do it this way is because if I was to run a chromatogram that was, say, 10 centimeters, and let's say this RF factor of the red component was 0.8. If I had an RF factor of 0.8 for this red component, that means the solvent front would have been 10 centimeters, and the distance travelled by the A component, which is our red component, would have been 8 centimeters. So 8 divided by 10 equals 0.8. If I was to then go do that experiment a week later under the same conditions, but except that I run the chromatogram to be 100 centimeters, then my solvent front would be 100 centimeters and my red component will have travelled 80 centimeters, because assuming that all the conditions are the same except that I ran the distance of the chromatogram 10 times as much, then the RF factor should be the same, 0.8. And so you can have different distances travelled for a chromatogram, but the RF factor should be the same considering the conditions are the same. In thin layer and paper chromatography, you often have standards that you actually run alongside your unknowns. So here I have standards, and the idea of standards is you know what the components are within the sample. Basically, I've put a sample here, and a sample here, and then I've run the chromatogram, or chromatograms in this case, and I know the components within the samples, and so they are called standards. Now you can have mixed standards that you've got 3 or more different components within the same sample, but you know what each component is. So these are all known. And what you do usually though is you actually run your sample of known components right next to your unknown sample. So this is our unknown sample. But because it migrates to the same distance as our sample of known components, and it actually runs to the same distance as the green component in the known sample, then we can actually say that this green component in the unknown sample is most likely that same component in the known sample. Now we're getting on to column chromatography, and that involves not only the crude method that you can see here in this picture here, but column chromatography also represents HPLC and GC, which is what we'll get onto later. But with the crude sort of method where you've got a glass tube and silica beads, you use gravity to run your sample through. So if you look at the schematic in the center here, we have a heap of silica beads which represent our stationary phase, and we have our solvent which acts to run our sample mixture. So that's our solvent, and that runs it's used to carry our sample mixture through the stationary phase using gravity to separate the components. And you can see that component 1 here, it's most strongly adsorbed to the silica beads, which is our stationary phase. Component 2 is less strongly absorbed, and component 3 is the least strongly absorbed to our stationary phase. We also have a porous barrier which prevents the silica beads from travelling down any further, but this porous barrier allows the solvent to travel downwards using gravity. And so we elute our eluent, which will contain different separated components at different points in time. The more volume that we actually run through our column, the more we separate our components, and the more we can actually elute. So with column chromatography, there are different properties that we can actually have with our stationary phases, and that can help us to select for different components within different sample mixtures. The chromatography procedures that are conducive to this, being able to change the stationary phases, are TLC, standard column chromatography, which is what we just looked at before, this picture here. GLC, which stands for gas chromatography, and high performance liquid chromatography. Now the properties of the actual beads that make up the stationary phase can be changed to be very polar, as in normal polarity. They can be very non-polar, as in reverse polarity. They can be very charged, either positively charged or negatively charged, depending on the beads, and they can be selected for, the components can be separated according to their size as well. So in the first type of stationary phase, normal polarity, what happens is you have a polar group such as an OH group, a hydroxyl group, and it's bonded to a silicon atom on the silica. And so when you run your sample mixture down through the column as we have here, if I've got a polar functional group on my silica beads, polar functional groups or polar components are going to adsorb very strongly to the polar functional group on the silica beads. So the blue component absorbs the most strongly. The red component, it's come out first, and that's because it's adsorbed the least. So the least polar, which means it's the most non-polar, will adsorb the least, and therefore be eluted first. With reverse polarity, it's the opposite of normal polarity in that rather than being polar, our functional group being polar, we have a very non-polar functional group. And so here we have a very long hydrocarbon chain. It's an 18 carbon chain, and we can get different size carbon chains to determine the amount of non-polarity or reverse polarity that we want, and we can get the optimum amount of reverse polarity that selects for the that separates the components within a sample mixture the best. But in any case, with increasing amounts of with the increasing carbon chain, you get increasing reverse polarity, or you get increasing non-polar properties, if you like. So if I run our column here and we have our blue component, our green component, our red component, the blue component has adsorbed the most to the stationary phase because it's bringing up the tail. The red component has eluted first, and so it adsorbs the least. So it adsorbs the least to the stationary phase. And it adsorbs the least because it is the least non-polar, which means it's the most polar. So non-polar things like to interact with non-polar things. So if you have things like fats and anything with a long carbon chain, a long hydrocarbon chain, that will often be non-polar and therefore will interact with the non-polar carbon chain on a silica bead. And so that's why the blue component, which is the most non-polar or hydrophobic, it adsorbs the most to our stationary phase. And the green obviously is in the middle there. So with the stationary phases for cation exchange, we can either have an anionic residue attached to our silica bead, as in the oxide ion here. And what happens is if I have really positive components, things that are really positive, have ions themselves, such as a sodium ion, I can use the anionic properties of the silica beads to inhibit the positive components from travelling through the column. So one step that a lot of scientists do when they're trying to get rid of sodium in a sample mixture is they run it along a cation exchange column in order to get rid of the sodium ions. And basically the silica beads in those columns have an oxygen functional group attached to it. So positive things will be adsorbed the most because there's a negatively charged functional group on the silica bead. Again, the blue one is most strongly absorbed. And the red one must be the least positive, it's probably negative, and it's the least strongly absorbed. With an anion exchange, it's the opposite. The silica beads have a positively charged residue which interacts with negatively charged components, and therefore if we run the column, a negatively charged component will interact with or adsorb to the positive residues on the silica beads, and therefore negatively charged components will be inhibited the most, so they'll migrate the least fastest, if you like, down the gravity column in this case, and the least negative or the most positive components within a sample mixture will run the furthest or the fastest and be eluted first. With size exclusion stationary phases, you have a heap of tunnels in the beads, and what this does is the small molecules can actually travel through these tunnels in the beads, and you can actually define the diameter of the tunnels within the beads as well as the diameter of the beads. And so you can determine what size components you're going to separate within a sample mixture and how much you want to separate them. So if there is tunnels within the beads, the small molecules end up travelling through the tunnels, and as a result they actually take a longer path length than the larger molecules. So the larger molecules go round the beads, and therefore that's a lot quicker than actually going through all the tunnels, because the tunnels can make you go all different ways as you're going down through the column. And therefore, as we run our column, our chromatography column here, the blue component, which is our smaller molecule, that adsorbs more strongly to the stationary phase, whereas the larger molecules, they travel around the stationary phase, which is the tunnels, I guess in this case, they adsorb less strongly. And here you can see another schematic. Now, I'm showing this because I actually have a number of different test tubes that are collecting a specific volume. Say if they're all collecting, say, 5 mil of eluent, which would contain our solvent and our sample mixture, we can actually run our solvent through the column, and we can have our sample mixture here, and as it's separated, the large molecules, as in size exclusion, column chromatography, the large molecules are eluted first, and we can actually collect them within a specific, a much smaller volume, and they're now separated from our small molecules, which are in a different test tube. And you can actually graph the amount of solute according to the volume of eluent, or effluent as they call it in this picture. You can graph that. Now, in high performance liquid chromatography, often there are columns such as shown here that actually have silica beads packed into them, and under high pressure you can run sample mixtures through these columns to separate the components within them. So there's often a pump within high performance liquid chromatography that forces the solvent containing the solvent and the sample mixture through the stationary phase. You can force the mobile phase through the stationary phase, and that separates the components within the sample mixture. Here we have a schematic of HPLC. So we've got our pump which forces the liquid mobile phase through the column. We have a solid stationary phase which is often made up of silica beads packed into the column, and what we do is we inject our sample. It gets forced down through the column and eventually gets eluted out the other side and is detected using a detector. Really common detectors for HPLC machines are UV detectors as well as mass spectrometry machines, which can then go and measure the mass of the components within the sample mixture. And obviously there's waste at the end of it. As well as that, the detector sends that signal to a recorder, and you can actually view the components in a chromatogram. So with high performance liquid chromatography, A mixture is injected into a steel-jacketed chromatography column and eluted with a solvent at high pressure. Now this is often 4000 psi, which is approximately 130 atmospheres. And if you think currently in the room that you're in watching this video, we're currently at 1 atmosphere, so this is 130 times that pressure that we actually live and breathe in. A solute's retention time in HPLC, the amount of time it takes to travel through the column, is determined by its interaction with the stationary phase and the mobile phase. HPLC can be used for both qualitative and quantitative analysis. And this technique is often used for purifying chemical compounds. It's also used for analysing air and water for pollutants, and it's often also used for monitoring pesticide levels in the environment. Sometimes there might be a dispute between farmers on neighbouring farms, and so they can actually work out who's responsible for killing the neighbour's really valuable crop. So here we have a gas chromatography machine, and you can see that this one has an auto sampler. So with auto samplers you can actually put your sample mixtures in these little holes in here, and you can actually go away overnight and it'll actually measure the various sample mixtures that you've put in the auto sampler to see what components in them. It'll actually run them through the chromatography machine for you. If you want to do it manually, there's also sample injection ports, and that's this spot here, which I've actually taken a photo of over on the left here. So we actually have 2 sample injection ports. And there's 2 sample injection ports because often you'll inject your unknown sample mixture along with a number of standard, a sample of standards, so that you can actually compare the peaks of your standard sample with the peaks of your unknown sample mixture. And the other thing about the injection point here is that it's really hot. You can see that by this symbol here. It's really hot, and that's because we want to vaporize the samples as we inject them into the chromatography machine. We're trying to turn them into the gaseous state. That's what I mean by vaporize. So what happens is your samples are injected in and then turned into a vapor, and a carrier gas such as helium or nitrogen is used to push the components within the samples through the chromatography column, and eventually it comes out the other end of the chromatography column and is detected either using a UV detector. In this case, in this picture, it's an MS detector, which is MS stands for mass spectrometry, and that's actually a mass spectrometry detector is what's often used in conjunction with a gas chromatography machine or a HPLC machine. So I'll sort of repeat myself a little bit here, but I'll just go through it. So a gas or a vapor mixture is injected into a very thin and long chromatography column. An inert carrier gas is then used to carry the sample mixture through the column, and that can often be helium or nitrogen, and the reason why they're used is because they are inert. A solute's retention time, so how long it takes for the solute to travel through the column in gas chromatography as in HPLC, is determined by its interaction with the stationary phase and the mobile phase. For the same temperature, mobile phase, stationary phase, flow rate, pressure and column length, the retention time should be the same for the same component in a sample mixture. So you can do different experiments, but as long as the conditions are the same, you should get the same retention time. So right now, if I was to run a gas chromatography experiment, I would need a mobile phase consisting of my helium or nitrogen. I would have to have a stationary phase, which would either be a dense liquid or a solid, and I would have to heat up my column to 300 degrees Celsius. This is in gas chromatography. You don't do this in HPLC. You only heat up the column to 300 degrees Celsius in gas chromatography. And you need to be very aware that the substance must be able to vaporize, however, not decompose. You can't use substances that decompose at 300 degrees Celsius. So you need to be wary of that. So then you inject your sample, and much the same with all the other chromatography experiments, you separate the components within the mixture. And you can see that here. So we had blue, green and red, and they've been separated depending on how much those components adsorb to the stationary phase of the column. Now with gas chromatography, I mentioned before about UV detection. That's actually used in HPLC. With gas chromatography, you would either use a mass spectrometer or you would use a flame ionization detector, and they're very sensitive. Here's another schematic of gas chromatography. You can see we've got our carrier gas, which is usually helium or nitrogen. It's forced through here. Then we inject our sample into the injection port, and then we put it through a very long column, up to tens of meters in length, and then at the very end it is eluted and detected in a detector, usually either a flame ionization detector or a mass spectrometer, and then we can actually graph those detections. So with gas chromatography, there are two main types of columns. There are silica packed columns, which have silica beads packed into the column, and this example here, this is an example of a silica packed column. Now you can see the diameter of this column. They can range between 5 to 10 millimeters, which is about half to 1 centimeter if you like. And they're packed with silica beads. And if I was to take a cross section and actually look at that, here we have a schematic of that, and imagine this blue part here that I'm circling here. Imagine that's the silica bead, and then attached to the silica bead is our special functional groups that I talked about before, in terms of normal polarity, reverse polarity, ion exchange and size exclusion. Imagine this green part is one of those properties, and you can see in this schematic that A tends to interact or adsorb very strongly to the stationary phase, which is what I've coloured in red here. And so A will therefore take longer to travel through the gas chromatography column, because it's always interacting with the stationary phase. Whereas B doesn't really interact with the stationary phase much. It likes to hang out in the mobile phase, and therefore will travel through the chromatography column a lot faster. We also have capillary columns. Now, in contrast to silica packed columns, which is this one here, capillary columns are a lot longer and they can be a lot thinner. And the reason why that's the case is because we don't have to pack anything into them. The stationary phase is actually the inner side of the column, and the stationary phase can be either liquid, it can be solid, or it can be a combination of a liquid and solid base, as in this option over here. But in any case, the stationary phase is the inner side of the column. So now we get to our gas chromatograms, and HPLC chromatograms are very similar in that you get an RT value for a specific component. So a component makes a peak in your chromatogram, as I'm circling here. These are all components and they all make peaks. And for each component you can look on the x-axis to see how long in terms of time, and in this case minutes, it's taken to go from one end of the column, from the sample injection port, right through to the other end of the column and being detected by the detector. And then it's put onto a chromatogram, a record sheet, as we can see here. So if I was to look at 1, 2, 3, 4 and 5, these particular components, I would say that 1 is approximately 6 minutes it's taken, 2 is probably let's say 7 minutes. 3 is approximately 15 minutes. 4 is approximately 17 minutes. And 5 is approximately 18 minutes in terms of their RT value. So if I was to give 1, 2, 3, 4 and 5 an RT value, a retention time value, I would give 6 minutes, 7 minutes, 15 minutes, 17 minutes and 18 minutes respectively. Now looking at our chromatography graph, again, they've actually circled down here, they've said that the hydrocarbons that they've put through the gas this gas chromatography machine, the first few hydrocarbons that have come out, they contain only a 4 carbon backbone, and then the next few is a 5 carbon backbone, and then a 6, and then a 7 carbon backbone. So as we're taking longer and longer for the components to get through the actual column and be detected, we're getting the components are becoming, the backbones are becoming larger and larger, so the molecules are becoming bigger and bigger. And the reason why the 4 carbon hydrocarbons are being eluted first and the 7 hydrocarbons are being eluted last is most likely due to the hydrophobic nature of the column. So the column's most likely hydrophobic or non-polar, if you like. So the bigger the carbon backbone, the more non-polar that hydrocarbon is. And if it's more non-polar, the hydrocarbon, which is a component in our sample, the more it will interact with a non-polar stationary phase. So I'm going to assume here that the stationary phase of this gas chromatography experiment was non-polar as well, because non-polar components, as in the 7 carbon hydrocarbons, are taking a lot longer to flow through the column, whereas our less non-polar or more polar components, which only have 4 carbons as their backbone, taking less time. And so that's how we need to think about chromatograms in terms of the stationary phase and the mobile phase. I could also do it in relation to size exclusion or ion exchange, or maybe if we're dealing with a polar stationary phase, it might be different. 7 might come out first and the 4 carbon hydrocarbons might come out last, but that it just depends on what properties a certain column has, because you can actually exchange columns in a chromatography machine. You can put in certain columns that specifically select for components that you're trying to separate. So in the second chromatogram, it shows a set of standards. So here we actually have 1, 2, 3, 4, 5. We've actually now this time run a set of standards through the chromatography machine, and we get clear bands at 6 minutes, 7 minutes, 15 minutes, 17 minutes and 18 minutes. So if we go back to our initial one, I could say that these peaks here are butane, 2-methylbutane, hexane, benzene, 2-methylhexane respectively, because they have the same retention time as my unknown. These have the same retention time as my unknown components in my unknown sample mixture. So we can use standards to work out. So that's a qualitative thing. We're using the gas chromatography machine qualitatively in this instance. Another thing you can do, if you want to just identify one particular component within an unknown sample mixture, you can actually add a known component. So this petrol sample has been spiked with benzene, and that's because we just want to detect if there's benzene present, and I guess if there's a lot present in this petrol sample mixture. If we go back to our initial petrol sample, you can see that the peak 4 is that large, and then when we spike it with benzene, peak 4 is a lot larger. So we know that peak 4 in our unknown sample is benzene. I can certainly say that. So that's why you run standards along with your unknown sample. Now, not only can we use gas chromatography machines for qualitative analysis, but we can also use them for quantitative analysis. Not only are we identifying what the components are, as in qualitative analysis, but we can also identify how much of each component there is. And so that's where we actually run a set of standards where we're dealing with one particular type of standard, such as benzene here, but we're changing the concentration of the benzene in our standard. So we run a chromatography experiment with 0.2% benzene, then 0.4%, then 0.8%, and then 1.2%. And then we run our sample, and we find that the peak of our sample, the peak height, and the area underneath the peak, because I know the peak height and I know the area underneath the peak of my components, they are proportional to the percentage, the concentration of that particular component. So what I can do is I can actually make a graph. I can make a graph like this. So with my different standards, I can actually graph them against the actual peak height and or the peak area in some instances. And then you can actually take the peak height of your unknown component in your sample, match it on the y-axis, go across to the regression line, this red regression line, because you'll always get a linear relationship, and then you go down to your x-axis and you can actually work out the concentration of your component that you're concerned with. In this case it's benzene. So we can use gas chromatography columns as well as HPLC columns for quantitative purposes as well.